Hello everybody. In this video we're going to learn about Ksp, which is related to equilibrium. It's going to have to do with the equilibrium for something dissolving, for how soluble it is. You can see here a chart of some Ksp values, and we will use these just like we used equilibrium constants. You're not expected to know what these numbers are. You will either be solving for this number or they will give it to you in the problem. The nice thing about this topic is that it's mostly review. Really, all we're doing are equilibrium calculations. We're using our ice tables, we're using our law of mass action. The thing that's a little different is that because all of these problems have a solid dissolving, your reactants are not going to appear in your law of mass action. But that's not actually something new, is it? We already know that fact. Really, the new part is just how we think about what we're doing. We're really going to start using the words solubility, talking about how much can be dissolved, looking to see which substance could dissolve more, which one might make a precipitate first, things like that. One thing to be a little bit careful of is that while most of our calculations that we do in chemistry, we use moles per liter, every once in a while you may see grams per liter in the charts. That's coming from kind of a practical reason. When someone wants to go make a solution, we often look at big charts and tables and graphs for solubility, and they show you how many grams you could measure out and dump into your container. So remember that our equilibrium calculations need to use molarity. So always double check your units. You may need to convert. And then it's usually represented by an S for solubility. When we do our calculations, we're used to putting X, right? You write minus X plus 2X. But if we're specifically talking about solubility, instead of using X, you will see people use an S sometimes. So here's an example. We have silver iodide. They give us the K value. We can see here from the equation that it's breaking apart. Because this is a solid, I don't even need to consider it in my ice table, do I? You'll often see people not even give it a column. I tend to give it a column and then put dashes through. It doesn't really matter. When we start, we don't have any that has dissolved. Nothing's dissociated yet. We're going to get plus X. Makes this nice and easy. If I want to write an equilibrium expression, you'll notice that my silver iodide is not there because it is a solid. I'm going to plug in my equilibrium values. I'm going to use the K value that they gave me. And I'm going to be able to solve for the solubility. This number tells me that I am able to dissolve 1.2 times 10 to the minus 8 moles of silver iodide in 1 liter. That's not much, is it? It's not very soluble. The higher this number, the more you can get to dissolve. The more soluble it is. All right, there's something a little bit tricky here. Take a look at this equation and try to set up your ice table. Pause the video, give yourself some time to set up that ice table. All right, we start with none, but this time if you look here, look at the coefficients. You gotta keep an eye on your coefficients in your balanced equation. Because now when I plug into my law of mass action, remember this won't be present. It's just going to be X times 2X squared because we had a 2 here. This is what we end up with. I would be willing to bet if College Board is going to give you one of these solubility problems, they're going to give you one where you don't have a 1-to-1 ratio. Because the common mistake we see is that people will get x cubed, but they will forget that they need to square the 2. A lot of people will write 2x cubed. But you have to square everything inside. This is the concentration. 2x is the concentration of chloride. And remember, we square the concentration. So that's where the 4 is coming from. So I've just seen repeatedly that this is the kind of one they love because this problem's not too difficult. But if you forget to square the 2, then you're going to get it wrong. So this is how much lead chloride we can dissolve in a liter. One thing that tends to come up in these KSP problems that doesn't come up as often in a normal equilibrium problem is something called the common ion effect. And what the common ion effect is going to look at is how does our solubility change? How do our answers change if we already have one of the ions present? If there's a common ion already floating around. So stop and think, pause the video, and try to figure out whether you think this would affect the solubility by increasing it or decreasing it. All right, if you already have an ion present in solution, think about Le Chatelier's principle. It's not going to want to make a bunch more if there's already something present. So it's going to decrease the amount of your solid that can dissociate. So let's take the exact same problem we just did with our silver iodide. We have our KSP. We know how much can dissolve. And let's put some iodide already in our container. And let's see if our 1.2 times 10 to the minus 8, if our solubility ends up greater or less than. So this time, do you see that I have a salt present? And the salt has an ion in common with the silver iodide? That's the common ion effect. So this time I'm not starting with 0 in both places. Now we already know that we get to use the 5% rule. Please make sure that you somehow are telling people that you're using that rule. Jot down a little note saying, oh, X is negligible, so I can use the 5% rule. I don't think that you need to prove that the 5% rule works. I think you just need to tell people that you're using it. So now if we solve for X, we can see, whoa, look, only 3 times 10 to the minus 15 will dissolve now. That solubility went way down. We're not going to get nearly as much dissociating because we already had some iodide present. All right, why don't you try this one? Pause the video so you have time. This time they gave you the molar solubility, but you are looking for KSP. So pause, set up an ice table, set up a law of mass action, and solve for what your KSP would be. All right, so this time I'm going to use S to represent the solubility instead of using X like we normally do, just to get you used to it. So you can see here, it's a 1-to-2 ratio. My law of mass action is going to be K equals the concentration of my lead times the concentration of iodide squared, and the concentration of iodide squared will have to take into account this 2, won't it? That's what I was reminding you of with that 4, right? We're going to get 4. And they gave me the value for the molar solubility, so I can plug that in to get my final answer. All right, just a couple of odds and ends to wrap up this video. The first is that they used to have us learn a lot of steps you could do, a lot of reactions you could do to test for the presence of certain ions. They would tell you things like, if you add this and you get a yellow precipitate, you must have lead chromate, present. If you follow these steps and you add these things and you get a white precipitate, you need to know that it makes silver chloride. We don't have to know all these anymore. Now, in college chem, it's very classic, very traditional to teach this to you and make you do it, and they'll give you an unknown and you have to try to figure it out. I want to make you aware of this because I want to make sure that if they give you a story problem and the context of the story they're telling you is about someone testing for an ion, that you don't panic and think you weren't taught something. It's totally fine. You're not going to need to know all of this to answer the question. At the end of the day, the question is still going to come back to stuff that you know. They're just trying to give it a little bit of a story. Okay? Another thing is that we sometimes run into weird things that can happen when you get these complex ions forming. So a complex ion can involve a metal cation. Those do a lot of weird things. Remember, we saw that some of those highly charged metal cations make things acidic, right? And ligands. Ligands can be simple compounds or they can be really weird things. But what they are Lewis bases that have lone pairs on them. And what they can do is they can bond with a cation and make pretty complicated molecules. These are the 3 that I could imagine might show up in some context. Now, they don't do a lot of Lewis acid-based stuff anymore, but they could give you a scenario and ask you to try to brainstorm why something might be happening. So understanding that because of the lone pairs here, these can make some complicated ions. You've seen that with like cobalt and water, right? Coordination number is just talking about how many of these ligands are stuck onto the cation. I just want you to know that term because I think it makes it easier to talk about. You might stumble across it if you're looking for extra practice online. It'll probably pop up in a textbook. Remember this, where we have 6 waters that get stuck onto that cobalt, and then that can cause some strange things to happen, right? So just a few examples. The reason I'm tossing this into the KSP lecture is because these weird ions that form can affect the solubility. And this is where I think maybe College Board would give you a problem that says, the solubility is lower than we expected. What might be a reason for that? And a reason might be that there could be some complex ions present that are affecting how soluble something is. So you could see here, this is what you would anticipate seeing. But that silver ion could do some strange stuff if you had a ligand present. Now it made this complex ion. And it can even add another one, right? So depending on what's present and depending on what's going on, you may have to take into account all of these different K values, and you end up with a different type of reaction truly happening that accounts for the more complex real-life scenario. They would never expect you to know that these are what's forming. But I do think it's reasonable to ask you to explain that sometimes it's not as straightforward as just step 1 up here. And that if you get these strange side reactions happening with these complicated ions, your solubility could end up affected. All right, everybody, that is it. I hope that was helpful. Bye.